Now look at geometric mean. Geometric mean is a geometric average of two numbers. So the way we place the geometric mean in a proportion is always in the denominator of the first fraction and then the numerator of the second fraction. So you build a proportion. So if you wanted the geometric mean between 4 and 5, x would be the geometric mean placed in the denominator and placed in your numerator. Then you would place 4 and 5 in either of the two positions that are left. Keep an equal sign because you have a proportion. So 4 over x equals x over 5. And you cross multiply. And when you do that, you get x squared equals 20. Then you take the square root of each side. Remember, you have to account for both a positive and a negative answer for x before it was squared. And when you simplify, you're going to get x equals to positive or negative 2 root 5. So that's what geometric mean is. Now, how do we use it? Similar to right triangles. Okay, well, the following. All altitudes of right triangles are the geometric mean. Okay, so we have two theorems here. The altitude of a right triangle divides the triangle into two triangles that are similar, and that altitude would be inside the triangle, the right triangle, making two triangles, a small and a medium. We're going to look at a picture of that in a minute. And then the other two altitudes, which are the legs of the huge right triangle, the big right triangle, they are also geometric means, and they are geometric means with regard to the hypotenuse and the part of the hypotenuse that is closely touching. So we'll take a look at that next. All right, so here is our right triangle, okay? So basically what we have here is, I'm going to take the green, move that down, is we have one big right triangle, which is green, and its side is x, one leg is y, and the hypotenuse in its entirety is u plus t, taken from AD, which is u, and segment DC, which is t's in length. Okay, so that's our big right triangle. Now, as you can see, we have a small right triangle here, which is has sides x, u, and z. And we also have a medium-sized right triangle, which has sides z, t, and y. Okay, so really we have three triangles in this one giant triangle in black here. Okay, so what we're going to do is pull this apart. So I'm going to take the small right triangle, ADB. Okay, I'm going to bring that down a little bit. I'm going to take the medium right triangle, and I'm going to rotate it so that they're all facing the same way. Okay, I'm going to spin it so they're rotating the face, facing the same way. And I'm going to take our green right triangle, which is the large right triangle. I'm going to move this over. And our green right triangle here, I'm going to move that off of here. And I'm going to rotate it, but I'm also going to get it facing the right way. Okay, that's where I want it. Okay, and I'm going to bring it this way so that we sync up to the right sides, the correct sides. Okay, let's rotate it. And I'm going to bring it over here. I'm going to rotate it a little more. What I want you to get out of this lesson is just an understanding of these right triangles and how they are similar to one another. Because you're taking it on faith and by just theorem definition and explanation that they are. Okay, it's about as straight as this is going to let me get it today. Okay, so as you can see, side in the small to the medium to the larger right triangle, the blue, red to green, the x, the y, and the u plus t are all hypotenuses. They are all similar in proportion. The u, the z, and the x are all in proportion, which is our bottom base leg. And our longest leg, z, t, and y, is also in proportion. Okay, so what that gives us, okay, is the following. If we compared the small to the medium, blue to red, we would have the ratios of u is to z, And if we looked at the side z, it would be z is to t. And if we had x, it would be x is to y. Okay? That's comparing the red and the blue to the red, the small to medium. If we compare the small to the large, okay, we would have the bottom leg, u, is to x. Z, the longer leg, is to y. And then the hypotenuse, x, is to u plus t. And if we compare the medium to the large triangle, we would have z, which is the longer leg, to, medium to large. Our z is here, our shorter leg to x, which is our shorter leg in our large triangle, so z to x. And our longer leg, t to y. And our hypotenuse, y to u plus t. And as you can see, in each one of these three ratios that we have created of, we'll call scale factors, of medium, small to medium, medium to large, and small to large, you can see where you have the same value in the numerator and the denominator. So u is to z as z is to t. Then we'll have another ratio of u is to x as x is to u plus t. And then we have another one of t is to y as y is to u plus t. And those are our proportions. So if we look at this, we can see if z is our altitude, okay, our internal altitude, it is the geometric mean between u and t. And here is our ratio right here in red. If we compared our small to large, okay, our geometric mean on the small is our hypotenuse is x, and it is the geometric mean because it is an altitude between u, which is the closest part of the hypotenuse that it touches, literally right here, it touches it, and the entire hypotenuse, which is u plus t. And if you look at our medium triangle, our hypotenuse is y, and it is a geometric mean because it is an altitude of the large right triangle. It touches this portion of the right triangle here, t, on the hypotenuse, and the entire hypotenuse, u plus t. So that's why it is t over y equals y over u plus t. And that's your geometric mean. So that's where you get the similarity of right triangles, and that's how you create your geometric mean formulas. So all your altitudes are geometric means. And it's important to know between what parts of the hypotenuse that it is touching. So if the geometric mean is internal, it's between u and t. If the geometric mean is on one of the legs, let's say x, it'll be u and the whole hypotenuse u plus t. If the geometric mean is y, it'll be on the part of the hypotenuse it's touching up to the other altitude, so t, and the entire hypotenuse. And that is how geometric mean works in comparison of similar right triangles.